All right, so we're going to just have some fun in this first video talking about discontinuities, which will define what that actually means, play around with some graphs so you can see what they look like, and I want you to just write down as I give you specific, we're going to talk about different types of discontinuities. Actually, let me see. There are 5 different types, so if you want to even right now just write like 5 bullet points down in your notes and save some space to draw a little bit of a picture of a graph that goes with it. That's really what you're going to want to do for this first video. First, let's talk about what I mean when I use the word discontinuity or discontinuous. We're talking about graphs. So we have 2 options. We can have a graph that is continuous or a graph that is discontinuous. A continuous graph you could draw it with your pen without ever picking it up from beginning to end. Obviously, it would be infinite, so technically we wouldn't be able to do that, but thinking theoretically, you could draw the entire graph without ever having to lift your pen. That's continuous. Discontinuous means that at some point along the way, there's a break in the graph for which you have to lift your pen and move it somewhere else. So it could be a hole in the graph, which we talked about a little bit in some of our prior lessons. It could be an asymptote, or, well, we'll look at what kind of, I don't want to give it all away. Without looking at our graph. So there are many different ways for us to cause discontinuities in a graph, but the question is, what are they? And then, of course, why is that important to us? Why do we care? So let's take a look at this lovely graph of the function y equals x. So actually, right here, we just have the function y equals x. This is about as basic as it gets when we talk about continuous functions. It's just one long line, not that interesting. We never have to pick our pencil up. It's just pretty easy to draw. In fact, I actually could, let me take this one off for a second, and another type of continuous function might be like the graph of x squared. So that's a great example of a function that you can draw from beginning to end without having to lift your pen. You could do the graph of, let's say, like a polynomial or something. We'll do x plus 2, x minus 5, x plus 6. Oh, we need one more just to make it slightly more interesting. And let's do x minus 1. There we go. Okay, I'm going to zoom out because we clearly need a little bit more space here. Oh, I created a very, very tall graph. I wonder if I can, I'm sure there's a way for me to, well, let's not mess with it right now. Okay, so as you can see, this is one of those, I'm only showing you out like this because I want you to see that there is no break in the graph. It's just kind of like a zigzag function, like it's just going up and down and up and down and up and down. But it's still continuous because we don't have to lift our pen to draw it. So that's, I'm going to delete that because we don't need it. Those are some examples of a continuous function, which I think, it's about as easy as it gets. There's nothing really interesting about a continuous function. However, let's say we find the graph of a function like this one. It's x squared plus x over x. And as we talked about in an earlier video, we actually had one very, very similar to this. This appears to be just a normal straight line. However, we know, because of what we understand about algebra, that if we're dividing by x, there's a possibility of dividing by 0. And when we divide by 0, we expect there to be some kind of interruption in the graph. So what I have here is this point A. Make sure I have the right clicker here. So as I drag this, you can look over on the left side. It's going to tell me what my coordinates are, x, y. So right now I have 1.53 and 2.53. And I can continue to drag it up and down, and it gives me all these different values. We want to know what happens if x is 0, because that's when we expect there to be a problem. So I drag it right down, and right there at 0, the point disappears, and A turns out to be what we call an undefined point. This undefined point, which is really an infinitely small hole in the graph. That's why you can't see it without dragging the point across it. There's this infinitely small, exact, specific spot when x equals 0 when the function ceases to exist. And what we call that is a removable discontinuity. So a removable discontinuity, that's your first type of actually, I told you there's 5. There's actually 4. My first type, I was just looking at my notes, is continuous function. So if you want to write down, it's possible to have a continuous function with no interruption. Secondly, it's possible to have what we call a removable discontinuity, where there's a hole in the graph that's just been taken out. Everything else about the graph looks the same. It just looks very normal, peaceful, nothing exciting going on. But at that one little spot, and again, we'll just go back to it because it's kind of fun to drag that cool little point, or if I can find it now. Oh, there we go. Ah, now I'm actually moving the function. Let's not do that. We can move it up and down, and we can see that when we drag it to this point, a becomes undefined. Okay, so next, let's talk about, let's take off this green function, and I want us to look at the graph of 1 over x squared, which is also a graph that we've talked about in prior lessons. Why is it valuable to us? Well, because it is an example of a discontinuous function. If I zoom out like that last one, this is why I zoomed out on the other one, I want you to see that it eventually connects. See this one? It doesn't. It gets infinitely close, but it never actually connects way up there. It just goes off into infinity. And so, here we go, rearrange. This is another example of a discontinuous function. I must lift my pen in order to finish the graph. It comes up to here, goes off to infinity, and lift the pen and back down here towards 0. This type of discontinuity, it's not removable because we can't just remove a point like in the last one and make everything look normal. This is an infinite discontinuity because there's no way of repairing what is infinitely broken. Yeah, it sounds very sad actually now that I put it that way. But if you have basically a vertical asymptote in your graph, here it is again, then you are dealing with an infinite discontinuity. Okay, next type of discontinuity. We've talked about continuous functions, which has no discontinuity, removable discontinuities, which is just a hole, infinite discontinuities, and now check out this next one. Actually, I'm going to skip over this because it's just so exciting. I'm going to go to Q here first. This is called the greatest integer function. I don't know if you've seen it. Hopefully you've seen it before. You should have seen it before. This is, it's also called a step function. We have little breaks of the line. Let me actually get this point because you'll be able to see it better with the point. So we have this point B. And as you can see again over here on the left-hand side, it tells you it starts out at, let me drag it, oops, my arrow. It starts out at 0, 0, and the greatest integer function says that the graph will stay 0, see the y value stays 0, until we hit another integer. So when I get to the next integer, which is 1, it hops up, and now I'm at 1, 1. Then we continue at 1, the y value is 1, 1, 1, until we get to the next integer, and then hops up to the next one. Now the integer is 2, so 2, 2, 2, 2, 2, 2, 2, 3, and then 3, 3, 3, 3, 3, 3, 4, and it continues on upward. And it works also down here in the negatives. It stays -1 until it gets back to -2, and then it continues on backwards. So that is called, it's also discontinuous, right? Because we certainly have to lift our pencil every time we get to the end of an integer. We have to jump up again. This is called a jump discontinuity. I know it's like rocket science kind of naming here. So we had the removable discontinuity, we had the infinite discontinuity, now we have a jump discontinuity. And the greatest integer function is not the only example of that, but it's a very good example. Okay, last but not least, this one might be my favorite just because it's so outrageous. Let's get rid of those points there. Okay, this is the graph of sine of 1 over x. And just as you probably would have expected, we can't divide by 0. So expect something weird to happen around 0. And if we zoom in here a little bit, it's hard to see, right? We see that as we get closer and closer and closer, we have a crazy amount of oscillation that gets tighter and tighter and tighter. But if we were to actually try to get to the point 0, 0, it would not exist. That point in the middle is missing. It's not removable because there's something about it that's kind of almost infinite in a not vertical asymptote kind of way, right? The closer it gets towards the discontinuity, the more it oscillates. It gets busier and busier and busier. In fact, it gets infinitely busy as it gets towards that center point, but never actually touches it. So this insane little graph of sine of 1 over x is what we call an oscillating discontinuity, because oscillating means going up and down, right? So we're actually approaching a discontinuity not by going off to an asymptote, not even just by removing a point, but it's actually oscillating towards an error, for lack of a better way of putting it. So our 5 types of graphs: 1 is continuous. Second, removable discontinuity, that's when it's just a point that's removed. Second, we have a infinite discontinuity. We have a jump discontinuity and an oscillating discontinuity. And that's all we need to talk about in this section. Just make sure you have a list of those names, because we are going to use it in our work, our classwork at school, and make sure that you can identify them. And we'll practice our ability to find those discontinuities, because they do happen to be important most of the time, and also to cause us some trouble, because they do like to do that. All right, that's it for topic 1. You do have a topic 2 video following this.